Howdy, Chem Nerds! Welcome to day 76, the day we'd normally take our equilibrium unit test. You can see that there's a whole slew of things from the Chatelier to Q's to things like strip charts that you need to master for this test. So this is the last chance to find out if you know what you need to know, right? So I want you to draw and explain for each of these reactions, two fictitious reactions, reaction 1, reaction 2. You can see I've given you the KEQs for them. I want you to draw an energy diagram and a strip chart for both if you were to start with, say, 20 reactants and 0 products, right? So pause it, see if you know what you need to know, and then we'll double check to see if you got it right. Cool. Here we go. If we look at this, I've got my reaction going on here. We'll do reaction number 1 first. And with reaction number 1, I've got A plus B makes and breaks C. And it tells you that it has a KEQ of 25. All right, well, what does that tell me? Well, first things I notice, 25, that's a huge number. That's much bigger than 1, which means that this thing favors products. When it's, of course, favoring those products is when it's reached equilibrium, because that's a KEQ. So it tells me with this reaction, this thing definitely favors products, which means overall it favors what we call the forward reaction, right? It likes to go forward. And if it likes to go forward, that means it's easier for it to go forward. So that means that in general, that would be an exothermic reaction. It's a downhill battle. So drawing my energy diagram for that shouldn't be too bad. One thing that I have is a reaction coordinate, right? If it's a downhill battle, then I should be starting high and making my way low. There's my A plus B, my reactants. There's my C. And that means that this right here would be my activation energy for the forward reaction. And this would show that I have a change in the heat that's in the reaction, right? The delta H, the enthalpy of this. And it went from higher to lower, so that's a negative delta H, which tells me that the forward reaction is an exothermic reaction, right? That means that this extra gap, this difference, is the energy that's being released, and it's usually released as heat energy. This, of course, would only occur really, really well if we had enough energy to break those. So we'd have to have a total energy line, that green line on the FET, that would be above that to break those things. Do that, and you can snap those things apart at a much better rate, right? Now, as you can see with this, it favors making a lot of product, and that would destroy a lot of that A and B. So drawing a strip chart would look at the concentration over time, right? And we told you in the beginning of this that there are 20 of the reactants, that's the A plus the B, and there are 0 of the products, C, so they're not even in the way. And if this is a downhill reaction, it's going to happen fast. And how do we show fast on the strip chart? We show it with a steep slope, right? And then, of course, as we do that, as we destroy A and B, we would quickly make C, and then eventually, of course, they would flatten out. And as they flattened out, their concentrations would stay the same because at this point right here, they've reached equilibrium, and they reach the equilibrium fast. How do I know it's fast? Because in the forward reaction, it has a very low activation energy because it makes so much of that product. And that's why at the end of this thing, the C is a huge pile of product, and there's just a little pile of A and B, right? There's 25 times as much C that's been created. One thing I can see here is I drew this line with a really, really steep slope because the steep slope tells me that this has a high rate of reaction in the forward reaction. It's quickly destroying A and B to make C. That's why we end up with so much of that. Now, I could shift that if I change the total energy line, which doesn't give you this information, but you can imagine different scenarios. If I drop that, the reaction is going to happen slower. That's why we cook with heat. Feeling groovy? Feeling groovy. Going on to number 2. Number 2, of course, has got a little different story going on. It's got a little bit of D plus E makes and breaks F, right? And if we look at this one right here, we can see that this has a KEQ that is 0.001. Well, that's not a big number. It's less than 1, which means that for this one, it doesn't make a lot of product, right? In fact, it has a lot of reactant left over. So this reaction clearly favors going backwards. It favors the reverse reaction. It favors reactants, right? So when we say that, of course, that means that making products must be harder, which is a pretty good indication that the forward reaction must be an uphill battle. It's endothermic. So that means that if I'm going to draw my energy diagram, I would have to have an uphill battle, which means I'd start low and go high, right? Just like trying to get to my classroom. The D plus the E would be my reactants, and I'd be making some F. And we can see that for the forward reaction, the activation energy is huge. That's a big activation energy, which means it'd be hard to make the F. That's why there's very little of it and lots of D and E left over. The only way you could get up there is if you added energy into it, and usually we can use heat energy as a simple way to add that in and get them collide faster. When I do that, I can notice that my change in my heat of the reaction is positive. It's going up. Hey, if it's a positive delta H, that's endothermic for my forward reaction, right? So if I turn that into a strip chart, I would have concentration versus time. We told you that there's 20 D and E, the reactants, right? And there's 0 of the products to start off with, the F stuff, right? And then we can see that it makes some of the F, but it really favors the other parts. So this would, of course, well, it would level out, but it would definitely not cross over each other because at the end, there's far more D and E, my reactants, than there is my products, the F, right? And at this point, hey, it's leveled off its concentration. It's reached its equilibrium, but it did it slowly, right? And it did it slowly because it takes a high activation energy to actually do this. It's an endothermic reaction to go forward. That's why it didn't destroy a whole lot of that stuff. This would, of course, only work out if I switched to my nice green line. It would have to be a line that would get above the F for my total energy line to heat it up to make enough of that to be sufficient. You could make a couple of them, but not many, just by the chances of the collisions. So that, of course, is going to slow it down in its rate of reaction, which gives me an idea of, with it, whether it's an uphill or a downhill battle. In addition to that, I want to make sure that I add in here, well, this is a reaction. It's endothermic forward, so this would be my heat energy that I'd have to put into that thing. Likewise, for reaction 1, if I go back to it, this was a downhill battle, so heat energy should be coming out on that side. So hopefully these strip charts and energy diagrams, you're seeing the big story that's going on there. It's telling you about whether it's, burning a house down or putting a house together. This one's putting a house together. And that happens at a slow rate unless you got a lot of, liquidity, energy, money put into the thing. Same kind of idea. Now, that is just a small piece of what's on test today. You would, of course, jump into the test. Then after the test where you prove that you understand your heat transfers, your Le Chatelier's principle, a little bit of the Haber process, we would read an awesome article about chickens sweating like crazy and, panting like crazy and drinking soda. We'll take a look at that the next thing to come. Now, good news, of course, as we look into that, today you will hopefully take your equilibrium test, or at least in this next week, and that'll give you an idea whether or not you understand KQ, Q, Le Chatelier's principle, how to shift the reaction to do what you want, how to draw energy diagrams, how a strip chart can tell you the story of those, what Q is, the transfer of energy, and then how that links to breaking and making bonds and how you add up the differences. All right, good luck. Make us proud.